Welcome back, everyone, to the International Geophysics and Tectonics seminar. This was going to be our last seminar before the break for AGU because of speaker illness next week, but a colleague in the department is going to give the talk instead. So there will be one more seminar next week, and I'll send out the notification about that. And then we will break for the 2-week-long AGU extravaganza, and we will then I will take a little bit of a break over the holidays, and we'll come back in January. And so I sent out a link. If you have feedback about the seminar, things I could do differently to help improve it, let me know. And if you have recommendations for speakers, then please do that. Okay. So thank you all for joining us today. I'm happy to present our speaker this week, Adebayo Ojo from the Geological Survey of Canada, or Natural Resources Canada, up in BC. So thank you very much for joining us, Ojo, and whenever you're ready, tell us about seismic structures.
Yeah, okay. Thank you, Kitty. Yeah, so good morning, afternoon, evening, everyone, depending on where you're joining from. I'm so excited to give this talk, and I want to thank you for taking the time to join the talk out of your very busy schedule, I imagine. Yeah, so today I want to thank Kitty for inviting me. It's an honor. I actually do appreciate the seminar series. I've been following the talks here myself, and they've been very informative. And also, I really want to thank you for being a crusader of the diversity and inclusion. And I think you're not just doing the talk, you are also trying to, make effort to make sure everybody is included. And I really love those compilation of resources. I've gone through them myself, and I found them very useful. So today I will be giving a talk that is part of a big project that I think I started, that I termed the Continental Scale Seismic Study of Africa. And in the first part of the project, I did look at all of the stations in Africa and try to look at how well-oriented these stations are. And we found out that several of these stations are actually, not well-oriented, which could affect the kind of result we bring out from studies using different components. And that study was published in Seismological Research Letters. And this is the second part of that project. And here my goal was to, image the structures in sparsely instrumented regions of Africa. And in this talk, I would give you a detailed explanation about how I'm doing that. So I've been lucky to work with, great scientists in my career journey. And so in this talk, I have collaborators from different institutes. This is Oluwaseun from Stony Brook University. Oluwaseun actually invited me over to Stony Brook and provided the computational resources to do this work. And this is my PhD advisor, which I'm really grateful to, Nisidao. He took a chance on inviting me all the way from Africa as his first PhD student. And so it gave me a chance to be a seismologist. And this is Li Jiao from Peking University, my first postdoc advisor. And this is a colleague that I've been collaborating with a long time from the Chinese Academy of Science. And Onkar is my current advisor at the GSC. Yeah, so. Okay. Yeah, so I want to start this talk from the very basic things, very simple stuff. And I want to start by putting a constraint on your expectation from this talk. I know in the last series of talk, we've seen several studies studying, very deep structures up to the common to boundaries. And because I've used a very vague term in my title, I really want to put a constraint on the, kind of depth that we'll be looking at in this talk. So my talk is about lithospheric structure. And if you look closely at this image, the lithosphere is that brittle outer part layer of the earth which consists of the crust and the very uppermost mantle. And in terms of depth, I'm talking about something in the 100 kilometers depth range. And I think this is the very interesting layer of the Earth where, you know, from plate tectonics, yeah, this is where all of the interesting things happen, like earthquakes, mountains, and all of that. And if you from these very simple plate tectonic cartoons, we know that these plates, you know, do move on a geological time scale over an underlying plastic asthenosphere. And as they move past each other, they could, you know, transform boundaries. You know, they could release very great moments and lead to large magnitude earthquakes at convergent boundaries. The denser lithosphere do subduct between the less dense and characterized with a lot of mountain chains, and even decompression methane as the subduction goes on leads to a lot of volcanic activities as well. And at the divergent plate boundaries, we could see a whole lot of magmatic activities and forming of new crust taking place in those areas. And all of these activities seems to have shaped Africa, you know, a whole lot. And here my goal is to just give you a simplified version of the African tectonics, starting all the way from when all of these very cratonic queue, the cratonic units in Africa were first together, you know, to form what we know as the Gondwana, and later the supercontinent, the Pangea supercontinent. And most, you know, the present day tectonic framework of Africa is, you know, really driven by the opening up of the Atlantic Ocean and the Indian Ocean. You know, that's when the Pangea broke up, and this through the opening up of these two oceans that are bounding the east and the western side, and also the very slow northeastward movement of Africa, you know, colliding with the Eurasian plate. And these two main tectonic processes have kind of reworked all of these cratons, such that now in present day, the cratons are now well separated with characteristic mobile beds around them, and sometimes very large scale intercratonic basins, like we see in Congo craton having Congo basin, and West African craton having the Tanzania basin. And much more recently is this new interesting divergent plates that is forming along the East African Rift system, where the African is currently splitting into the Somalia and the Nubia plate. And we imagine that in millions of years to come, the Eastern Africa will have drifted away from the remaining part of Africa. And also much more, and we could see that such extensional tectonics is characterized with a whole lot of magmatic activities, and even much more outside these magmatic activities taking place. The continent of Africa is characterized with a whole lot of interplate volcanism hotspots in several other areas. For example, we have these chains of volcanoes that transect the ocean and the continent boundary called the Cameroon volcanic lines, which we'll talk about in subsequent slide. And we also have these volcanic hotspots, you know, in North Central Africa, which would also, you know, look at the later part of this talk. Another main feature that people are, you know, enigmatic feature in Africa is the very anomalous topography in the southern and eastern part of Africa, and probably this anomaly is about 1,000 meters higher than average continental topography, and so people have been trying to look at that. So I'm doing this because, you know, recently I did talk to my advisor, and he did share with me that, you know, I don't really know much about African tectonics, so I don't want to take a chance that everybody do understand this, and it's just nice to give a simplified version. What I've done here is a very simplified version. For a geologist, this will mean just like a basic explanation. So here I want to group all of these previous studies in Africa into what I call scientific questions that they've been trying to answer. Instead of, showing you, tons of studies, I just want to, pick sample studies and then group all of them under the scientific questions they've been trying to answer in Africa. So the first is a lot of studies have been trying to understand this anomalous high topography in Southern Africa, which if you see this contour, they are about 1,250 higher than almost every other places. And it transcends from the southern part of Africa to the eastern part of Africa. It's called the African super swell. And so there's been a lot of study to understand what causes, how how do this form in itself? What causes these topographic swells? And one thing you could notice that from several global tomography study is that there is this thermochemical plume rising almost from the core mantle boundary, and having a pathway, finding its pathway to Eastern Africa. And so there's a lot of consensus that seems to agree that probably this anomalous topography is due to the plume impingement, this large-scale mantle plume impinging on the South African continent, lithosphere in this, but much more in the eastern part of Africa, where there has been a lot of magmatism, induced rifting, like I showed in the earlier slide. There seems to be an understanding that this might also be contributing to the topography structure in this place. And recently also we have some explanations from isostacy uplift due to lithospheric delamination taking place in this region could also be contributing to some, or in some parts to this anomalous topography. Another interesting question is people have sought to understand what triggers this extension, that we have in the East African Rift, where Africa is now, splitting. And the interesting thing is, if you see Africa, on the two sides of Africa, we have actually spreading centers. And in spreading centers, you expect then that the main tectonic forces that should be affecting Africa now should be compression rather than extension, because you have a spreading center on this side, you have a spreading center on this side. So what you expect is compression. So people expect that, how come we have, kind of extensional tectonics taking place in this region, despite which is the opposite of what people expect. And from several tomography studies and seismic studies, there seems to be a consensus that there is this alpha plume, impinging on beneath the East African that has, eroded the lithosphere and found its way to create these chains of this rifting event here, and the formation of new ocean basin in this region. But the question here is the magmatic plumbing system is not really understood. We have models ranging from a single plume to multiple plumes, and some of these plumes are not connected to these large scale features, some are connected. And so there's a lot of debate in literature to particular, and this is an important one because, in our lifetime, you rarely would find places where a continent is rifting, and this is one of the natural laboratories that we have right now. So another interesting thing, feature in Africa that people are trying to understand is this enigmatic Cameroon volcanic lines. I personally also spent quite like 3 years of my life trying to study this volcanic chain during my PhD program. And what's interesting about this volcanic chain, usually like the Hawaiian chain, what you have is that you have a stationary plume source, and as the plates move over the years to different locations, then you have the plume impinging and finding hotspot centers at different locations as the plates move over geological time scale. And one particular characteristic of such formation is that you have age progression along those lines. But in Western Africa, where you have these CVL volcanoes, which is about transit the ocean and the continent side, and we have probably more than 15 volcanic centers that does not follow age progression. That means most of the traditional explanation for interpretive volcanism does not work here. And another interesting thing is maybe you could notice the bisecting, the preferred location of this rift, which bisect almost the Southern Africa, continent at this angle 45 region. And also you could notice this very field triple junction called the Benue Trough here, and the pattern of this feature and the pattern of this volcanic volcanoes. People have been used, people have constrained the basalt and the volcanoes in these regions, and I've found that they look very similar. So there's this idea that there's a common geodynamic controls on this feature. What's interesting about this is that in this place, we have little extensional tectonics. We have no evidence for rifting. We have no evidence for melt retention in the crust. We have very little modifications of the crust. And so every evidence that you have that should show you that this is, where the plumes are coming from is non-existent. So several geodynamic models proposed are not valid to actually explain this line. And recently there's been an increase in evidence to show that there's some small scale mantle convections that are taking place in this place, but several authors have been explaining this by different phenomena. For example, this model has tried to explain this from their tomographic result, where they see these very fast cratonic units, which is the northern portion of the Congo Craton, and these relatively slower locations, change along the CVL. And what the explanation is probably because of the different thickness in the lithosphere. We have what we call the edge-driven convection, where you have a downwelling beneath the thick lithosphere, and then rising to, and you have an upwelling beneath the adjacent regions, which is the CVL in this case. And from receiver function studies, they've come to know that because the 410 and the 660 discontinuity in the subsurface, in the deep mantle, seems not to be affected at all. They look very average structures. And so this put a constraint on the depth of where the origin of these plumes are coming from. And so it's been, there seems to be a consensus that this is an upper mantle plume structure. But there's a lot of debate about the exact mechanism. This is some of my studies where I've shown also that we have very fast velocity in the Craton Union and Craton region, and very slow velocities, relatively slow velocity along the line. And this particular study is what I really like. I did used seismic anisotropy studies from surface wave, which can give a depth constraint better than at least than SKS splitting studies, where you are not sure of where this depth of the anisotropy is coming from. And I see that basically the model supports this explanation, such that we have at the edge of the Congo Craton, we have almost non-anisotropy, meaning that there's a vertical flow. And you could see the pattern of the anisotropy, and on the Congo Craton, the direction of fast axis is similar to the direction of plate motion. But as you see this go to the along the line, volcanic line, you could see that the pattern of anisotropy and then changes to northwest southeast direction, which shows a more recent layering of materials in this region. Somehow I think to argue that this feature shows that indeed there's possibly the vertical downwelling going on at the edge of these cratons, and then upwelling along the line, like we'll see here. So another question people have been trying to answer in Africa is they've been trying to see if the cratonic lithosphere, formed like 2 billion years ago, have remained the same, or if there have been some extensive erosion of this cratonic lithosphere, and if there's been, what is the mechanism? you know. And so here I've shown two recent Nature Geoscience papers that that have shown this particular study. They compile a new global set of data using all of the recent stations in Africa, and they've been able to develop a new model of the lithospheric thickness beneath all of these cratons. And then what they did is to compare that to the locations of the diamond-bearing kimberlite and lithophite, which shows which is known to form at locations where the lithosphere is quite thick, you know, more than 150 kilometers. And they've compared that to the present day depth of the thickness of the lithosphere, and they found that quite several places where we have all of these diamond-bearing kimberlites in the past are now underlain by cratonic queues that are much shallower, you know, indicating that the total volume of cratonic lithosphere has quite reduced over time. And also this new this study, what they found is that this is actually the first study claiming to find anisotropy in crustal anisotropy within cratons. And this is a study in South Africa where they showed that they found very significant, measurable crustal anisotropy within the cratons, indicating much more deformation taking place. And because the fast statistics is, you know, is similar to that in the from SKS studies, the difference is almost zero, almost close to zero in most of the cratonic unit. They seems to propose that there's been a long-term coupling between the mantle and the crust in this region. So also in the last set of talk, group of study, this particular study is, you know, done extensively by the African Array Group. And what they do basically is, because the money of their deployment, they study the crustal structure. So most crusts are formed in the Precambrian, and Africa contains about 90% of Precambrian crust. So, and even Arabia also. So what they do in these studies is they measure crustal parameters like the VPVS ratios, the crustal thicknesses. They measure the thickness of high velocity layers in the lower crust, and they then compare it from between different Precambrian structures of different age. And basically what they're trying to find is if there's any evidence for circular variation in crustal genesis. This is quite important if you're doing geodynamic modeling of the origin of the crust. You want to place if there are different processes that formed the crust at different times, then you want to place more constraint on your model. So, but over time, there have been two groups of arguments, some finding evidence, some not finding evidence. But even if you don't find evidence, it might just mean that the crust has been reworked over time, that currently you don't have, the features that should separate them have been erased over time. You know, so this is much debate that is going on, but I don't think so. This study has shown from the youngest province to the oldest to the youngest, and they saw that the crustal thickness is variable within and among the tectonic regions, and also the layer of lower velocity, probably magmatic underplating and things like that, are also variable. So they didn't see, they found very little evidence for seismic circular variation in crustal genesis. And so most of all these studies that I've shown have usually I've used seismic tomography, which has been a very potent tool in the hands of seismologists to image the subsurface. And I like this. I want to show this interesting short clip from the Zurich ATH Zurich group that showed the importance of the source receivers geometry for you to be very successful using this technique. It is observed that for seismic tomography, it's data intensive. The more the data you have, the more resolution you can get of the subsurface. And so they've done a video showing how Africa, the model in Africa has evolved from about 3 decades ago as they have more and more data sets, more and more earthquake coupling and more stations are being deployed. And you could see that as more and more ray paths are traversing or crisscrossing the African continent, the model is, becoming much more improved until present day model, where they have very relatively, a large number of parts crisscrossing Africa, and then they have a model that seems to be much better constrained than the earlier time. Yeah, but this particular method, which is very potent, also have some current limitations in Africa, as you can see. So here I've taken data set for the last 3 decades, from 1990 to date, all of the seismic stations, global seismic stations. I've also plotted all of the large magnitude 5 and above earthquakes. And what you could see here, obviously, is that the African region, as compared to some other continent like the ambitious US Earthscope array, which almost cover all of the continent of all of the US all of the expanse of the US. In Africa, what you see is that we have very sparse station coverage, especially in the north central and northeast western part of Africa. And so what you have is all of these small scale temporary deployment, which are deployed by network managers to study specific structure. For example, this small array was deployed to study the Cameroon volcanic line. This small South African seismic experiment was to study kimberlites and all of this cratonic, and many of these small scale deployment to study the East African rift. So over time, there's been a non-uniform coverage of the African continent. And also, if you notice, the yellow dots are the earthquakes. You could see that for 3 decades, you can't even find one large magnitude earthquake in all of this part of Africa. And that means local tomography is not possible. And even for large-scale studies that have recent large-scale study, this is a comment from the recent study of the model that I've shown earlier, and you could see that there's a comment here that despite the improvement, I mean, they combine a lot of data sets, and even new arrays in Africa, the station coverage still remains uneven and sparse. And you could see the number of parts they could retrieve across the African continent. You see that it is in the lower end of the color scale in most part of Africa. And this is another study using another type of data set, ambient noise data set. And also this study noted that despite the improvement in data set and methodology, they use full waveform inversion, and they found that the structures, they couldn't recover very, very small scale structure that has not been seen before. So that which then brings me to the second part of this talk, where I want to show you why we then need, it's obvious to everybody now that there's need for a better model, which would benefit from more data set. But for me, why we need even better models in Africa is because we need to better understand how these shallow dynamics relate to deep mantle dynamics that we've been seeing. And also there's been a lot of geodynamic model explaining possible channeling of plume from one side of the continent to another. But if we don't have a continental scale structure model where you could check if this relationship also exists, then you can place a constraint on several of these mechanisms. So I think for a more complete understanding, we need a good model that constrains both the shallow and deeper structures, and we also need a uniform model across the continent that shows the inter-provincial tectonic province. And how do we do that? I think the first way to do this is to densify the seismic stations in Africa, like you have for the US array. And obviously that's ambitious because obviously there are economic constraints. And I remember myself, running up to every Pascal station that I see when I go to conferences and ask them, oh, I learned you guys give stations to be deployed. I want to deploy stations in Africa. Can you give me, how does it work? And also I remember going to GFZ and asking them, I want to deploy, can you borrow me some of your stations? It's quite expensive, and you need a whole lot of collaborations to do that. So the next thing I thought about is, we've had studies from earthquake, we've had studies from ambient noise data set. Can we combine both data set, to possibly improve the model? And if this is obvious, then another question came to my mind: why have other people not done this over the years? Yeah. So in this part two, I would explain, how we build a new model and the general features of the model. So the first thing I did was to take the metadata, because it's a lot of data set. I don't want to waste a lot of time processing all this data set, and at the end of the day, the model is not in any way improved, or we don't have better constraint to structures. So what I did is to take the metadata of all of available stations, and which show, and the seismic catalog. And the first thing I wanted to know is how many of these stations have enough duration of deployment that could ensure that we will have a lot of earthquake data set recorded, and we will have a good amount of length of data set for ambient noise cross correlation. So if you see, all of the stations I found across Africa, I see that at least, so most of all of these stations were deployed for about 1 to 2 years, which I think is pretty long time to retrieve a good kind of data set. Another problem that I sought to answer is that because the ambient noise cross correlation method means that you can only work with stations that have overlapping deployment times. Yeah, so I wanted to know how many ray paths, how many stations, can we have that over the lifetime of each station, and how they overlap with all other stations in the continent. And I saw that if I put a constraint of 500 days of overlap between two pairs of stations, I see that I could retrieve almost 67,000 parts, theoretically speaking now. Assuming all of this data is good enough and all of the stations are working throughout their deployment time. But one thing I could see is that there might be possible problem on this edge of the continent, as you could obviously see too. And also I wanted to know how many magnitude 5 and above earthquake would all of these stations have recorded in their lifetime. And I found that at least most of these stations will have recorded more than 200 seismic earthquakes greater than magnitude 5. And I think with all of this, it satisfied my curiosity that this method can help improve the model in Africa. And so here I'm showing you what I did finally. I took a lot of about more than 3 decades of data set from IRIS DMC, and these are the stations, and I retrieved continuous ambient noise data set for all of this time period, for the deployment time period. And I also took retrieved data set for magnitude 5 earthquakes that happened in epicenter distances of 30 to 120 and happened shallower than 100 kilometers, because I'm using surface waves and I want them to be, the shallower they are, the better defined they are. And so you could see this global, obvious global compilation of data set that I'm using here. And one of these, the thing I also want to find out is if these two data sets are compatible. Because if you combine data sets that are not compatible, then you're introducing a lot of uncertainty into your model, which then might mean that your uncertainty is even probably higher than your perturbations. So one thing I did is to see if for this station and other stations, if the cross correlations are similar. And you could see that just for this one example, you could see that the cross correlation retrieved from the ambient noise data is quite similar to those retrieved from the earthquake data set. And also you could see the distinct similar phase velocity retrieved from the cross correlation. And obviously you could see the sensitivity of dispersion to different structures where, across these magmatic regions, you see very slower dispersions, and probably in other parts, you see much faster dispersion. And another thing, generally for all of the data sets, I compared at overlapping periods of around 10, 20, 10, let's say 15 to 40 seconds. I compare the differences in the velocities from the two-station method and the ambient noise method, and I see very nice normal distributions that are well constrained. I mean that shows very small differences. Also, although some of them show very there are some outliers at the end, but for majority of the data set, we have almost a mean of about 0, which shows consistency. So combining this data set, I could see that if I use just ambient noise data alone, I could retrieve maximum of about 20,000 parts. If I use earthquake station data alone, I could retrieve probably about 30,000 parts. But if I combine the two data set, I could retrieve almost up to close to 50,000 real parts, which is quite close to what I obtained when I did these synthetic studies. So combining this data set, I wanted to see how much improvement I was able to achieve. And although there are critics of checkerboard test, but I think in combination with the ray part density, you could begin to see where your model has very good sensitivity. So at the shorter period end of the dispersion, we could see that where we have stations, we have good recovery of the checkerboards. But in regions where there are no stations, there seems to be some sparing of the feature, and you could see that is also justified by less ray parts density. But as we move to longer period, we could see that at this checkerboard 3x3 checkerboard, we could retrieve almost a uniform structure across all of the continent of Africa. And we could see that the major improvement is in this north central part of Africa, where we have rays crossing from these stations in the southern part and these stations in Europe. And this also, I showed some of the tomography results here, which just to show you that there seems to be, consistent pattern between the group and phase velocities and some small scale differences where their depth sensitivity is quite different. And also the fact that we are very good struct anomalies that correlate well with where we expect features to be. For example, the large scale intercratonic basins are shown as very nice slow velocities, and even the basin in the Mozambique channels. We also can see fast velocities in the cratonic regions, and so we have very great agreement with known tectonic features, which give us confidence about this model. And so just to give you a general feel of what this model it looks like, at the shallow end of the model, we could, I took the average upper crustal velocities here, and we could see that, like I said, very slow velocities in regions where we have deep sediment thicknesses, and also in places where we have deformations like the West African Rift, the Central African, the Central African belt. We could see all of these very slow velocities, and even in the northern part of the continent where we have a whole lot of deformation due to collision, and also we have fast velocities underlying the cratonic regions, and even in the Congo craton, in the Cagliari craton, the Tanzanian craton, and all of that. And so one of the things, and even in the Arabian region, you could see this very slow velocity in the northern and northeastern part of the continent as compared to the part that is closer to Africa. And you see also very deep sediments in the Mediterranean basin here, and which is far thicker in the eastern side, than the western side. These are features that are well aligned with previous studies. And I tried to constrain the thickness of the sediments in this region, and we could see that we have sediment thickness up to about, even 14 kilometers thick in these regions. And, we could see also in the Saharan desert, we have quite some thickness of sediment thickness in this area, and even the basins here. We have some good constraint on the sediment thickness, but probably best at regions where you have good resolutions and the basin is quite large. At the lower end of the model, I'm showing you the uppermost mantle model, and you could see obvious slow velocities along the mobile belts. The West African mobile belt, the Darame orogeny here, and you could also see where we have cratonic roots. We have fast velocities in this region, and also even along around the ceramic craton, you have these fast velocities aligned. And in the East Africa, where we have mantle plumes, you could see the very relatively slow upper mantle velocities, and also beneath the Red Sea and all of these features. And one of the things also that and also in Arabia, you could see that the upper mantle in the northern side is quite fast compared to the southern part of the continent. And one of the things I try also to constrain is the thickness of these the thickness of high velocity structures in the lower crust, which could give us an indication of where we have magmatic underplating, and if the cratonic roots beneath all of this craton are still existing or not. And you could see that, if beneath like the Zambia craton, that like it's been shown in the previous studies also, that the fast velocity in the lower cross upper mantle region seems to have been eroded in beneath some of these cratons as compared to some of these other cratons. And so if you're interested in more details about this new model, I shared a preprint online somewhere at this address that you could take a look at our interpretation of many of these structures. And so this brings me to the last part of this talk, which I would, focus more on this region, where I think this is the main achievement of this study, where we have better new constraint to structures in this region where we have almost little or no stations. And in this region, there are important features. For example, this is the region where we have the Sahara metacraton, which and the formation and the destruction of craton is one important topic in geoscience community. And also the interpret volcanism taking place here. And these are two interesting topics that I think we can address with this improved model in this region. So in this third part, I will be intimating you with what we found in this region. So like I said, in the Pan-African orogeny, all of these cratons were thought to be together. As you can see, before the continent, South Africa drifted away, but with modern day opening up of the Atlantic and Indian Ocean, you now have the craton that has been reworked or remobilized. Move apart and then they now have these characteristics orogeny belts or mobile belts all around them. But for this region where we have the Sahara craton, we could see that this craton seems to have particularly suffered from several tectonothermal events, related to collision between all of these cratonic bodies. To the east of it, we have the Tuareg Shield. To the west, the Arabian-Nubia Shield. To the south, we have this Congo craton. All of these, at one time or the other in time past, they've collided together, and also the collision of the general African plate to the Eurasian plate. So there seems to be some suspected cratonic remnant. That this craton has actually been decratonized, but there seems to be some suspected remnants in this region, and this feature shows where the inferred boundaries of those remnants are. And one obvious thing that have not allowed geologists to be able to observe, put a constraint on this is the very thick sedimentary, the sediments that has covered these remnants. And so we have all of these three sediments that are supposed to be suspected to be underlain with cratonic remnants. And so people have been trying to understand structures in this, but the structures in this region have been poorly imaged and studied because of the limitations in stations and resolution of previous tomography studies. So I narrowed down on this region, and I tried to see, take a cross section across the different remnants that has been suspected remnants. And what I found basically is that we do see for the Akufra basin, and you could see that in profile A and profile D, we could see, for example, very relatively thick sediments in the near surface, about 5 kilometers, and which deepens to the northern side of the inferred boundaries of the craton. And obviously we could see these high velocity localized bodies in the as you can see here, also in the much shallower crust, and which is much constrained to the southern part of the boundary of the inferred boundary. And we could also see obvious high density. So this observation is supported by the very relatively high density Bouguer anomaly, showing that there's these mafic bodies exist in this region. However, beneath the Shad Basin, as we could see in profile 1 and also profile B, we could see very quite different settings. We could see that obviously the sediment is much thicker beneath the Shad Basin, but beneath it, it's underlain by mafic bodies that are much deeper, probably the basement or the intrusions from and generally we could see in this region that we have very fast lower crust in all of these, along all of these profiles. And so also beneath this region, we could see very fast velocity, upper mantle velocity, which is the main differences in all of these remnants. We could see that beneath the Akwafra Basin and the Muzak Basin, the upper mantle is quite slow, but beneath the Chad Basin, the upper mantle velocity is quite fast, and the differences is also shown in the Bouguer anomaly that we see beneath the Chad Basin. The Bouguer anomaly is quite indicative of a low density region compared to the high density regions of these two other basins. And in the last basin, the sediment is quite thinnest in this basin, very thin, about 2 kilometers, and also exhibits some existence of localized high velocity body in the lower crust in the region. And also likewise, the velocity, upper mantle velocity is slower. And also we could see the very high density Bouguer anomaly. And so what I've realized is that the differences in the similarities in these two remnants seems to have been very affected by this hotspot that is quite close to them. But this very cratonic remnant, suspected remnant, is quite much farther away from the hotspot center. So there seems to have been much more reworkings of the cratonic lithosphere beneath these two basins by these hotspots more than it has affected these other cratonic remnants, suspected remnants in the region. And so also I took a nice look at each of these hotspot centers in the region, you know. And in the first one, I see the Darfur Dome that we can see here. And we see that in the upper mantle, there is quite, you know, unique upwellings beneath all of these topographic swells representing the hotspot centers. But one feature that you would see that is not constrained to this dome. You will see the pattern of structures in the upper mantle is that we have these high velocity regions and then very slow velocity region almost adjacent each other. That shows, and our interpretation is that first we observe unique mantle upwelling beneath each of these hotspots, you know, as we can see. But we imagine that they may be connected to a much deeper, you know, mantle plume, you know, that is then that what we now see in this, all of these hotspots are just preferred lithospheric weaknesses where the mantle plume can be erupted into the subsurface. Because if you can see, this is one of the mantle plume track, and you could see that we seem to have very, you know, obvious evidence of tracks of these previously tracks of probably melt in the crust that are now cooled, you know, and you could see all of these kind of features all around the upper mantle and the crust, the lithospheric structure in this region. So so what we want to then do is given all of these results together, what can we say about the geodynamic? Can we put a constraint on the proposed geodynamic models for the destruction of the Sahara metacraton? And one thing is there are 3 end models that has been proposed for the destruction of this metacraton, and the first is the improvement of deep plume, and the alpha plume is a candidate model. And there has been also another model that favors reactivation of large-scale shared zones due to the collisions. You could see this is the craton, West African craton that has once collided with this craton, and to the south, this is Congo craton, and there are also other sheet bodies, and in the north also there is this African Eurasian collision that has been happening, and so there's a suspicion that this could have created a lot of large-scale shear zone in the region that you know destroyed this particular craton, and also this has also been linked to recent extensional tectonics along the East African Rift. You know, but taken together, I think from our model, what we see is that we see evidence for extensive modification of the lithosphere by widespread volcanism, interplate volcanism at this hotspot center, especially the Tipesti hotspot and the Uga hotspot here. And we think this extends magma. There seems to be lithospheric denomination as a result of this improvement of plume in this region, which have then led to the total removal of the cratonic keel, at least in the certain portion of the Sahara metacraton. And one very quite remarkable observation that I want to talk about is that we found that, yeah, beside, and the question is now, where is this plume coming from, right? So people have said probably the plume is from this same alpha plume, probably channeled through zones of lithospheric weaknesses to this place, possibly because you could see different path route that are of slow velocities, you know, across all of this region. This is one possibility. Another possibility is that we see is that we seem to observe these edge-driven convection that might be happening at the edge of the Congo craton here. If you see, this is the high velocity, you know, similar to what we observe in the Cameroon, for the Cameroon volcanic line. There seems to be this downwelling beneath at the edge of this Congo craton, and then upwelling in the adjacent mobile belt in this region, probably feeding some of these volcanic center through lithospheric channels of lithospheric weakness created by all of these collisions that has happened. So we you know, our observation favored that, you know, you have extensive Cenozoic volcanism in this region, but the plumes are then channeled through zones of lithospheric weaknesses created by the several collisional events. And so that's my story about the central part of Africa. But what more are we doing actually? The first thing we want to do is to obviously our model needs further improvement. You know, models always need improvement, right? And so one thing we're doing right now is to include more data sets. Yeah, the data set used in that in building that model was up to the mid 2018. And from then till now, that's almost 2 years of more data sets. And we also think probably there are now more open stations because there's always an embargo on some of these stations and they are released over time. And also one very important thing that we are doing is we see that we need longer dispersions to be able to constrain much deeper depth. For example, I just said probably the plumes are connected at depth, but right now we can't say. And so with longer broadband dispersion, we'll be able to image much deeper into the mantle and then understand this. And also we're thinking of improving the resolution of our study in the northwestern part of Africa, where we see that our model is not doing well, by including stations in South Atlantic, you know, and also we're doing a lot of joint inversion studies with multiple seismic data set. Here I show that we've retrieved receiver functions data and the much really wave electricity data set that is much sensitive to very shallow structures in this region. And we're combining all of those data sets to, build a high resolution 1D models beneath all of these stations. And also, lastly, we have all of these. We see that our dispersion didn't quite constrain the crustal thickness so well. The sensitivity of surface wave dispersion to the crustal thickness is not as strong. And also in comparison to models from gravity studies and compilations of the Crust 1.0 model, we see that there's quite large differences between these models. And we think we could improve this model by doing a joint inversion of the potential field data and the seismic data set, and also in the future invert for anisotropic structures and using body waves and seismic surface wave together. And so I will leave you with these conclusions that, if you're interested in studying structures, Africa continent is one place to go. I believe there's a lot of nature paper to be published in this region, and that we show that we've developed a new model that have good constraints to structures in sparsely instrumented areas. I also show that we found evidence for cratonic remnants and that these individual unique upwellings beneath the mantles, plumes that may be connected at depth. We show that there may be some edge-driven convection beneath at the edge of the West African craton, and that both widespread volcanism and collisional tectonics are likely involved in the destruction of the Sahara metacraton. Yeah, so these are some references. Thank you, and I'm open to questions and comments.
Thank you. That's very cool stuff. Min Chen, you have a question. I see your hand raised.
Yeah, I will only ask one question. Is the 3D model already published and available through IRIS, EMC?
Not at the moment. We just submitted a paper to JGR, and in that paper we also stated that our goal is to contribute this model to the IRIS DMC. I've been talking to Susan about this as well, and we hope to do that. Yeah. But there's a preprint of the paper online, and the model itself would be contributed to IRIS.
Yeah. By the way, I would like to collaborate with you on all the future studies if you want.
Very great. I want that. I remember there was a time you had a postdoc offer at the end of my PhD, and some of my colleagues in the group, were busy, competing for your position. Yeah, and so it will be nice to work with you on some of these things. Yeah.
Oh, thank you so much. Let's keep talking afterwards.
Yeah.
Ed Garnero, you had a question.
Yeah, thanks for the great presentation. I learned a lot. I have a question about other kinds of seismic waves, like multiple SCS, these kinds of things that we've been kind of on a campaign measuring those in the past couple of years. You might need to embed your region of interest in a global inversion in order to deal with where those waves are affected by other structures. But do you have a comment on it? Would those help that central part of Africa that has where the coverage is not really that great?
Yeah, I think I would think there has been a lot of studies that have attempted using all of these other type of seismic waves that could have bounce points and beneath the African continent. And I think, you know, the problem is that most of them, I think, have very good constraint at deeper depths. Yeah, like the, you know, deep mantle or the sub-lithospheric mantle, you know, and of course, I think they would help improve. I think the way to improve this model will be to then take these these new models that are more sensitive to near surface and then combine them with such data set like you're saying. And then we could see the whole complete picture, probably. Yeah, so I think it would be a combination of those kind of data sets and this new kind of data set.
Cool, thank you. And if you want, I could show you some of that work.
Oh, great.
Later.
Yeah, thanks.
May I ask a question?
Yes, go ahead.
Yeah. That was a very impressive presentation. You got an awful lot of models and a lot of understanding from considering that the coverage of Africa is so small. I was very interested in the rapid variations that we saw in the thickness of the crust in some of your profiles.
Yeah.
And I wondered if you see similar scales of variation looking under, say, the United States, where you have much data coverage.
Yeah, I have not actually looked at models, you know, beneath US, but I see one of my collaborators, Winston, has done extensive structure studies beneath the US. And I think the US has very remarkable high resolution model, but I think what they see is very distinct more in the southern and the eastern parts, you know, and probably some small scale studies, you know, would show some of these remarkable more differences, you know, but I have not, you know, intimate myself with recent studies about the mole thickness. I'm sorry about that. So probably, you know, there could be, it's likely, very highly likely. Yeah, but as for pointing to a particular talk or paper, I don't have one at this time. Yeah, sorry about that.
Yes, as a follow-up, one of the reasons for my question is presumably the African continent as a whole is in isostatic equilibrium. And I'm just wondering how this was achieved. Obviously, there's some variation across the thickness and some variation in upper mantle velocity and mantle velocities and so on. It's obviously very complicated. If you had to select one area of interest to follow up in detail, what would you say was the most interesting thing that you've seen in your data?
Yeah, I think in my data, like I showed here, and it will be my very follow-up study, is that I'm suspecting that there is, you know, these, you know, what I call small, probably small scale, probably large scale, mantle convection, edge driven. You know, this is the Congo craton, and we see beneath this Congo, at the edge of this Congo craton, that we have very fast velocities deplete, you know, which is consistent with this craton. But just adjacent of this, we see these very slow velocities, you know, next to it, which I'm thinking there is a downwelling at this edge, and there is, you know, an upwelling next to the adjacent, you know, lithosphere, which is probably less thicker, in terms of probably this is driven by the differences in the lithospheric thicknesses between these two regions. But why I'm want to follow up this is, as you see, I've plotted a dashed line around this model, showing where we are the most sensitivities from our current data set. And that, this region falls at that boundary, And so I want to be sure, of course, this is true that this is a craton. We expect fast velocities, but I want to be very sure of the fact that this feature actually exists, because when I took a profile across this feature, I see very great, as in very pronounced mafic, underplating, and a whole lot of pathways of magma, previous magma, because most of these magma, I think, are not very active right now. The velocities are not that very slow, So it would be nice to trail, if this is true. And one way I want to do that is to include data set from South America on this side. Then I could have more ray paths crossing all of this region. And then I would be able to put very, great confidence on what this structure is really. Yeah. And I think geodynamic modeling also would be a good one to do. Yeah. If we confirm that this is not artifact, which is not likely.
Yes, another question. If I remember rightly, when you show your profile across this line, across this structure, there seemed to be a step in the mantle, a discontinuity, a vertical.
You mean this? Oh, no. This is the only profile I showed anyway. And this. These are the two profiles I showed in this talk. Yeah, and probably what you're saying is the only thing we'd see, for example, is this beneath all of this cratonic region, you could see the obvious crustal thickening that is happening due to mafic underplating beneath where the volcanoes are finding their pathways into the crust. You could see that we are very mafic bodies that has accumulated, and then that showed up like if we are very thick crustal thickness beneath each of these volcanic hotspots regions.
Thank you very much. That's very interesting.
Yeah.
Wish you well in your future studies.
Yeah, thank you. Yeah, thanks for your questions.
Thank you for that. Alex, you typed a question in the chat. Would you like to ask it? Or I could just read it. So it was asking, what would you say accounts for the lack of stations, particularly in the West African region, and what could be done to help improve the model in this area?
Yeah, like I said, the lack of stations in West African region is, I think is also related to lack of interest in studying the structures that are there. I think most of these stations in Africa are deployed by international partners, with fundings with project fundings, let me use that word. And for example, if you take an NSF funding to study CVL, you're not only going to deploy stations around the CVL structure, right? And also if you get a funding to study continental riftings, you then going to put your station in this. So I think lack of stations in this region is because people have not had interest in studying these other structures that are there. And because the African, the seismological community in Africa is also still young. I mean, not so many people are into seismology back in Africa. And so probably there's limited resources or push for government funding to fund deployments as well. That would be my take on that.
Yep.
Oh, what can we do to help? yes, if you do have connections to Pascal array or all of these large scale arrays, and we could deploy stations, please contact me. I will be happy. But I think the African array funding is over now, and there are new teams taking up that. And I think I'm very sure they are pushing for new proposals that would probably focus on these other areas of Africa. You know, yeah, probably.
Thank you. So there's two hand raised. Kent Gandhi, would you like to ask your question first?
Very exciting data, Oko, in an area that we don't have a lot of information.
Yeah.
In terms of the Sahara metacraton,
Mm-hmm.
this has been very controversial, as you point out.
Yeah.
And I was wondering if you had considered an alternate interpretation. Bob Stern and others had suggested that much of this area may be actually juvenile Neoproterozoic crusts that formed at the same time as the Arabian-Nubian shield area did, say 600 to 800 million years ago. And that there was really not any Archean craton here at all, ever.
Mm-hmm.
But the three fast roots you have there, the Muzuki and the Al-Kufra and the Chad, maybe just three remnants of Archean crust that was trapped during the accretion in Neoproterozoic of a large origin that extended from Central Africa clear over to Eastern Arabia. I was wondering if you had considered that possibility.
Yeah, thank you for that. In fact, as you talk, I just recollected as you're talking that honestly, my interpretation has an assumption, and the assumption is that there was a craton here before. And like you said, there are also models that suggest that there is no craton here. These are just materials amalgamated, together, that then looks like we have some of these remnants, in this region. And that's a viable alternative. In fact, they call that explanation the simple way out. Just you don't want to say a craton was decratonized and what is the mechanism. You just want to say these are just materials packed together over time and remnant. Yeah, and that's very viable, I must say. That's very viable because in here it's not like Southern Africa that you have kimberlites that you could use to constrain the fact that probably the lithosphere was quite thick at the time. So going back, you don't have evidence to actually say this craton was there actually in reality. And thank you. I must include that alternative model in my interpretation and to say, okay, if we assume there is a craton there, this is what we think. If we assume there are no craton there in the first place, then this might be what we see. Yeah, thank you for that. Yeah. Yeah.
Thank you. Chi-Che Chen, would you like to ask your question? Oh, you are muted right now.
Yeah, thank you for the talk. And I want to ask one question. And based your model, I noticed some strong velocity anomaly around the Madagascar island. So do you have any explanation about it?
Yeah, and I would quickly show you this figure. Yeah, you could see in my talk and also in my paper, I refused to really talk about Madagascar Island.
Yes.
And this is the reason. And this is the reason. There are many stations, more stations that I used in this study in Madagascar, but at the time they were not open.
Okay.
But I think now many of those stations are open. They are deployed by the GFZ in Germany. And so I think personally that constrained the limit of interpretation that I should be doing there. And you could see, but notwithstanding where those anomalies are located, you could see that notwithstanding we have very good some sensitivities, in those areas. Yeah. As you could see, especially at longer periods. So if I have an Upper Mandu structure in this region, I should start believing it, right? you know, and you could see my lines of locations where they are well constrained enclose this region. But I haven't, as you said, I have not really thought about what these structures could be. I've only just ignored them anyway.
Okay.
Yeah, so I think because my focus was really in this region, you know, but possibly in few, as we refine the model, and if this structure persists, then I think we would consider an interpretation. But you know, and thanks for pointing my attention to that as well.
Thank you.
Yeah.
Thank you very much. We have another question from the chat. Nuha, would you like to ask a question?
Yes, thank you for your presentation. I'm just very interested about the blade motion around the area of the East Africa Reef System, since I work with the Red Sea and Gulf of Aden right now. So I just see from your general model feature that you didn't say a lot about why it is separated, the east and western branches of the East Africa Reef System. Do you have any kind of evidences regarding that?
You mean, sorry, again, why they are separated?
I mean, the East Africa Reef System is kind of east and western branches, right? And the Victoria microblade are in the middle. So do you have any kind of evidences from if it is Afar bloom, if it is kind of another reason? If we assume that Afar is kind of migrated to Hajar area to the west? Yeah.
Yeah, okay. Yeah, thanks for that question. I would possibly go back to this slide. This slide. Yeah, and you could see that, like I said on this slide, and this particular study seems to address some of your concerns. Yeah, if we say this is alpha plume, you know, and this is the head of the plume, and if we assume that the reach of that plume would be possibly around one kilometers, then the question that has been asked is that if we say this is alpha plume, then how can we explain that the alpha plume can reach from its source here way down to these locations? You know, and that's been the question that, you know, that, for example, in this study, they've constrained the reach of this alpha plume to about a radius of 1,000 kilometers, which probably geodynamically, this is the range of distance that plume can cover from its very initial, from the alpha region. And so there are quite more probably reasonable to say that there may be some other features, you know, plume responsible for this the southern part of the volcanism. And what I imagine really is that if we say this is actually connected to the to this large scale large shear velocity provinces, then I imagine that this location might not be the only preferred lithospheric weakness zone which this magma may erupt to the subsurface. So possibly, you know, over time, as you have all of these plume impregment and you have more weakening and rifting, probably there are some other locations in the southern part that respond to these weaknesses that then the same plume that you have can then find a way to erupt and then, you know, cause much more opening up in this region. So if it could be one plume, you know, expressing itself at different locations of lithospheric weaknesses, you know, or it altogether, which is what I would think that is more viable, because if you say it's another kind of mechanism, then you have to then explain it. For example, the mantle small scale, the mantle convection models that has been also used to alternative model of explanation, I don't think they would probably be able to drive the level of magma that we, you know, explain the level of magma that we have, you know, in this accompanying the riftings in this region. So I would just think possibly this is the same plume, but expressing itself at different locations of lithospheric weakness. That would be my explanation.
Okay, thank you. Because previously I was thinking about the Darfur dome itself, you know, if it was connected to AFAR itself or not, because there is some kind of 1 or 2 publications try to kind of, explain about Darfur dome. So that's why your presentation was really interested. Thank you so much.
Yeah, thank you.
Thank
you very much. Are there any last questions for Dr. Ojo?
May I just make a comment on the last question? A plume known as the Nyanzan plume has been postulated for this region, just to the northeast of Lake Victoria, to explain the volcanic history of the rocks in this region. It's a complicated story, and I wouldn't attempt to explain it now, but that idea has been postulated.
Great. Thanks for that.
Thank you. Yeah. Thank you all for the great questions. And let's thank Dr. Ojo again for the wonderful talk.
Yeah, thank you.
Well done. Very good.
Yeah, thanks. Thanks, everyone.